Institute of Engineering and Technology.
Hello students, in this talk we are going to cover from positive to negative term by term. It is known as alternating series. We have also seen alternating series in detail with its test of convergence as Leibniz test. Now at the time of this alternating series, I told you that there are different possibilities of convergence. Like it may happen that a positive terms and negative terms individually they are moving towards zero by decreasing its nature, and that only we are going to use in Leibniz test. But now it may happen that the given series is not convergent by its absolute values, but whenever you take that series as a whole, they are converging towards a value in form of that residual number which is generated by reordering or repairing the terms of series. So in this case or in this discussion, we'll focus on that special type of convergence which is known as conditional convergence. So let us start that part from infinite series as conditional convergence. So how to define this conditional convergence? To define conditional convergence, we need this thing that if our series un is convergent but its absolute series is divergent, that this looks bit unfamiliar at a time, but this is also possible whenever you are dealing with a random series which is changing its positive and negative values term by term. That means I'm talking about alternating series. So in such cases, that series is known as convergent conditionally. Now how to go through this conditional convergence, or where actually it is produced in between our regular convergence and absolute convergence. So if I focus that, if I take a mode of values, it is known as absolute series, and if it is convergent, obviously the series is convergent, but the converse is not true. It may happen now that our regular series is convergent but its absolute series is not convergent, and that case will give rise to this conditional convergence. Another possibility is that every convergent series of positive term is also absolute convergence. That means now there won't be any role of this magnitude taken on the series. Ultimately it will remain convergent. So if series is positive term series, absolute convergence is our regular convergence. What do we mean by this alternating series or this conditional convergence graphically. Let us go through our first case. First of all, I am considering alternating series. You can see clearly here the values above x-axis given by this blue bar, they are nothing but the positive terms of the series. And the values which are below x-axis given by blue bar, they are nothing but the negative values of the series. Now if I want to check whether it is convergent or not, I need to check by Leibniz test that their values are in magnitude decreasing term by term or not, and then they are approaching 0 or not. This is what actually we are doing with help of Leibniz test. But now as we know that by considering magnitude of this value, it will give you another series in which we have all terms in a positive way. And then there is another case of convergence which is known as conditional convergence. And to make that thing clear, now what I will do, I will reflect all values which are below x-axis by a value on the upper side of the x-axis. And then you can see the values are decreasing term by term now. But now this simply means that they are pretty much close to each other in a consecutive index value n. So now if I go for the pairing of these two terms, means a term which is given by red bar and a term which is given by purple bar. This red bar is nothing but negative by nature and the purple bar is nothing but positive by nature. If I pair these two, there will be a quantity and a negative sign and then another quantity. So by taking that subtraction in that pair of two number, it will give you a new number, and that residual value will give you totally a new graph or new series. If that series is convergent, we can say that our given series is convergent, but with condition, that is we are rearranging our terms or we are reordering our term. So I hope this part is clear now, that what do we mean by conditional convergence graphically. For that, let us consider one example. If I want to check whether this alternating series minus 1 raised to n plus 1 into n square upon n cube plus 1 is absolute convergent or it is conditional convergent. Now see, it is very much clear that if we are considering alternating series, we have these two possibilities. Absolute convergence means the given series with its absolute values is convergent. But now we have another possibility also, that if the absolute value of the series is not converging, it may happen that series as a whole is convergent by rearranging the terms in a pair by considering that the residual value will obey the rule of convergence, and so it is known as convergence with condition of rearrangement, so it is conditional convergence. So obviously we need to first of all check conditional convergence. How we can check this conditional convergence? So at a time I am considering the given series directly. As it is alternating series, we need to apply Leibniz test. So for the Leibniz test, I am considering my first condition, that is mode of an is strictly greater than mode of an plus 1 for all n greater than some number capital N. And as we know that to check this decreasing nature, we are always defining function f of n. And then by taking its derivative d by dn into n square upon n cube plus 1. If I take derivative by applying the quotient rule of differentiation, it simply gives me 2n minus n raised to 4 upon n cube plus 1 whole square. Now this is strictly less than 0, as denominator is always positive, but numerator is quite negative with the heavy part or the bigger magnitude on n raised to 4. So it is on a negative side, and therefore the value overall is less than 0 for all n greater than or equal to 1. This means that my derivative is negative, and so the function is decreasing by nature, and therefore the given series is decreasing term by term. Now let us check second part. If I take n tends to infinity, it simply gives me 1 upon n into 1 plus 1 by n cube. As we are dealing with n tends to infinity, I need to take maximum value of n from numerator and denominator, and I need to cancel that part. So from numerator it is n square, from denominator it is n cube. So n square is cancelled with n cube, and therefore if I take n tends to infinity, it gives me answer 0. This simply means that the values are 0 whenever this n is approaching towards infinity. That means now we are satisfying both conditions of Leibniz test, and this gives me that the given series is convergent directly. But now we need to check whether this convergence is conditional convergence or it is absolute convergence. So now what I will do, I will bifurcate this convergence into two parts by considering the mode of the values in the given series. If that magnitude series is convergent, we can say clearly that it is our regular convergence. But if that magnitude series is not convergent, we can say that it is conditional convergence. Now I will show you first of all graphically what is happening in this series, that why actually this series is convergent. You can see the graph of n square upon n cube plus 1, as it is alternating by nature. The values are positive and negative with reference x-axis. Now as they propagate from n equal to 1 to infinity, you are seeing clearly that both of this positive series and negative series individually they are decreasing by nature and they are approaching value 0. But now what will happen if I take mode of all these values, which we did actually in case of Leibniz test? You can see clearly that they are decreasing now as I reflected all negative values towards positive, and it is approaching value 0. So this simply means that it is convergent directly with help of Leibniz test. Now let us move to the second part to check whether there is actually absolute or conditional convergence. So for that I need to check its absolute convergence. So for absolute convergence I am taking mode of this. So it gives me simply n square upon n cube plus 1. So now my series will reduce into summation n equal to 1 to infinity n square upon n cube plus 1. As we have polynomials in numerator and denominator, we can always select comparison test. So now if I take comparison test, I need to identify the dominating part, and to identify the dominating part, a procedure is to take maximum value of n from numerator, maximum value of n from denominator, and after simplifying we have that term 1 upon n which is remaining as a dominating part, which will add this series towards 0 if I take n tends to infinity. So that means the dominating part is 1 by n. So we should assume new series by 1 upon n. So if I assume summation bn as 1 upon n, then by limit comparison test n tends to infinity, an upon bn, this is equal to 1, and that is a constant number. That means now the nature of this series summation bn is simultaneous with summation an. So if bn is convergent, an is convergent. If bn is divergent, an is divergent. But now we can see clearly that this series is going to be a divergent series, as this series summation bn is divergent p series. In fact, it is a harmonic series. So that means the absolute value series is divergent, but we have already seen that its regular series is convergent. And that means this convergence is nothing but conditional convergence. So this is the case where we can exactly say that the terms are not moving towards 0 in case of absolute value, but they are moving towards 0 in the form of the residual value by rearranging the terms. And then you can see clearly that why it is diverging. If I consider magnitude series, then all the values are now reflected in the positive way, and then initially the values are decreasing, but then what will happen after a certain level, the values are containing 1 upon n as a subseries. So that means now we have a series which contains a divergent subseries, and so the given series is divergent which is nothing but the mode of given an. And that simply means that my series is convergent directly, but if I consider the magnitude value, they are decreasing by nature. And so it is convergence with a certain condition of rearranging the values. So it is known as conditional convergence. So I hope all of you understand this idea of conditional convergence. It is quite complex. You need to repeat this video at least 2 to 3 times to understand the meaning of convergence, meaning of absolute convergence, and meaning of conditional convergence. So remember, whenever you have positive term series, you have root test, ratio test, integral test, nth term derivative test, and then Rabi's test. Whenever you have alternating series, you have Leibniz test. And to check whether given series is absolute convergence or not, you need to take absolute series for the given series, and we need to check its convergence in a regular way. And if you want to check its conditional convergence, you should move towards 2 different possibilities, regular series as well as its magnitude series. In upcoming discussion, we'll see a special category of the series as a power series. We'll also see radius of convergence. Thank you.
LJ Institute of Engineering and Technology.